Okay, section 1.8, linear transformations. All right, let me ask a question. How many remember when you learned about functions, you had domain and range, and a function maps, when a function if you have f of x equals x squared, okay, if you do f of 3 equals 9, if f of x equals x squared, if that's your function, if that's your rule, and then 9 is the image of 3. How many remember terms like that? Thank you, Marvelous. Domain, range, image of, okay, yes, Eleanor, yes, Eleni, excellent. Thank you, Abby. So section 1.8 basically talks about transformations in that kind of language. Okay, that kind of language. You can think of like they had show up here an example where you take a vector x and you pre-multiply it by matrix A. Okay, and that equals then the vector 5, 8. So what you're doing is you're transforming a vector x into a vector b. Okay, and what you're doing is you're taking a 4x1 vector x, a vector that lives in R4, and you're mapping it into R squared. Similarly, here's another example where you take a vector u and you map it into the 0 vector. Okay, so this figure 1 very nicely shows what you're, in terms of symbolically, what you're doing. You're taking vectors x and u in 4-dimensional space and you're mapping them into 2-dimensional space. Okay, so you're used to like mapping numbers to numbers, you know, but with linear algebra, with if our transformation is a times x, if that's your transformation, if your function equals the matrix A times a vector x, and the function is a function of the vector x defined by the matrix A times a vector x, you can map vectors in one space to vectors in a different space. Like you see right here, you're taking x and u, which live in R4, and you're mapping them into vectors that live in R2. Okay, and so, you know, it's really quite an amazing thing, and it's a mapping. It's a mapping. So just like with functions, where you map elements from a domain into a range, with transformations in linear algebra, you take vectors and map them from a domain and map them into a range. So like for instance, in this example 1 here, you have this matrix A. It's a 3 rows by 2 columns, and you have vectors u, b, and c, and they define this transformation that maps vectors from R squared into R cubed, from 2-dimensional space to 3-dimensional space, by a times x. In other words, that's your function, your transformation. You take the vector x and map it into this, you take this vector x and transform it by taking the matrix A times the vector x. And you can see that you're taking a 3x2 matrix and you're multiplying it by a 2x1 vector. That then is going to become a 3x1 vector. Okay, so in part A, they want you, for instance, to find the image of u under the transformation. So that's easy. the image of u under the transformation would be the vector 5, 1, negative 9. For part B, find a vector in X whose image under the transformation is B. So the B vector is 3, 2, negative 5. So to answer that question, well, this is the setup. You're looking for a vector X, x1, x2, such that A times X equals B. It amounts to solving a system of equations. And this is your augmented matrix. You do the row operations, and you will get out a solution. So the vector X, which equals 1.5 and negative 0.5, that is the image of that vector is the given vector B. Are there any questions so far? We're very close to being done here. Are there any questions on this concept? It's really just like functions that you've learned, only you're working with vectors and matrix multiplication. Who's feeling good so far? Okay, thank you, Benjamin. Thank you, Abby. Thank you, Naima. Wonderful, wonderful. Okay, well, let's continue on. For C, they ask, is there more than one vector X whose image under the transformation is B? Okay, well, any X whose image under the transformation B must satisfy this equation. But there's only one, we only got one solution vector, 1.5 and negative 0.5. So there's exactly one X whose image is B, exactly one. Okay, exactly one in this example. Okay. And then finally, determine if the vector C is in the range of the transformation. So here's C. And you want to see if that's in the range of the transformation. So what you have to do is you have to see if the vector C is in the range of the transformation, then C is the image of some vector X. So you have to see if there's a solution vector X that will work. And it turns out that you get an inconsistent system. And so C is not in the range of the transformation. It's not in the range. Okay. So these kind of questions are questions you've seen before in terms of regular functions, but now you're working with functions of a vector X. And the function of the vector X, the functions of vector X are traditionally, they don't have to always be, but A times X. Okay, that's a matrix transformation. Are there any questions on this idea, at least initially? I know you have to practice a little bit with it, but are there any questions? Okay, well then I will stop the recording.